Hello, welcome back to my computer vision series. Today we are going to talk about DAB Detr, or Detr with dynamic anchor boxes. So if you are unaware of what that is and where that stands, that's a little diagram to help you out. So we are solving object detection task, high resolution images, Colco dataset, several objects in the picture, and you don't know how many in advance, and you need to draw the actual bounding boxes and class predictions for every object. And in my channel before this video, we have discussed the YOLO, which is an old school model using convolutions and some handcrafted components like non-maximum suppression or anchor boxes. And then after that, we've discussed the Detr model from Facebook research that simplifies the fundamental structure of the model, allows to train it end-to-end in just one go without handcrafted components, but it's much worse. So it's a huge model. It trains maybe 10 times longer, but the actual precision is below that of just YOLO. So what's the point, right? But then we can see on the diagram that several improvements actually make it so much better than anything else you could have on the market that you know that it's really worth it. So in the previous video, we also discussed deformable Detr. Now we discuss Detr with dynamic anchor boxes, or DAB Detr. And then in the future videos, I hope we'll also discuss various other models like denoising Detr, Swin, vision transformers, Dino, and finally current state-of-the-art CoDetr. Here's the plan for today. So first, we're going to discuss motivation behind dynamic anchor boxes. So how did the researchers came up with the idea? What are the fundamental problems we're trying to solve? And then just go through all the main parts of the model itself. So we're going to talk about what dynamic anchor boxes are and how are they useful as object queries. We are going to discuss how they affect the prior of the positional attention, how they modulate the side attention in the decoder, how they are updated dynamically layer by layer, and finally, results and what's next. So let's start with the motivation behind dynamic anchor boxes. So this is the picture from the original Detr paper. So we start with the backbone, which is just a convolutional neural network. We feed in the image, and as an output, we get a downsampled version of the image. So it's more condensed, it has more processed information, and so we want to use that in our detection model. Then we have transformer encoder, which basically flattens the image out and then computes these pairwise interactions like we do in self-attention to create these more refined representation of the image. And deformable data that we've discussed in the previous video targeted the encoder mostly by saying that we don't actually need to compute attention between every possible pair of pixels because there's just too many of them, and that's a huge limiting factor. Because of this, it's too computationally expensive and we can't afford high resolution pixel maps. So what deformable data does is it says that we just need 4 points instead of all the pairwise combinations. And now we want to focus on decoder. So this is the decoder. So in decoder, we have object queries coming from the bottom. And if we recall what attention actually does, is you have queries. In this case, they come from the actual queries. And then you have keys and values coming from the encoder. And then you use queries and keys to compute this attention mask that basically tells the network on which parts of the image to focus attention on. And then the actual values are used to compute the output, and the attention mask is used as weights for these values. So main purpose, or should I say the only purpose of these object queries is to participate in this attention process. So to tell the network where to pay attention to. And so in the original Detr, we just used random trainable vectors as object queries. So we initialize that randomly, train it with the network itself, and then just, it sort of works, but as we know now, it doesn't work as well. We've also seen this picture. So this is the representation of attention from these queries on the last layer of the decoder. So when image is already well processed, so right before the output, right before we are ready to actually tell the bounding box for the object. And you can see that it looks quite well. So it looks like it's focusing on the proper areas of the bird, because to actually draw the precise bounding box, we need to know where the tail is, where the legs are, where the head is, because these are the extreme parts of the object that actually control where the precise bounding box is. But then the researchers came up with this question. So what happens in the earlier layers? And maybe what happens when the network is just starting to train? And this is actually the most important image from the original paper for DAB Detr. So the title of the paper actually says, dynamic anchor boxes are better queries for Detr, which means that we don't need anything else. We just use dynamic anchor boxes, and they are better than anything else you can come up with. And this is why. So this is the attention map for few initial layers of the model in the middle of the training. So we can see it's not as good. So it might have two blobs focused on two different points. It might focus on something up top and then something up bottom at the same time, which is not really good because we don't really have objects like that. So all our objects are localized in just one location. They can be big, but the center of the object is always in some one place. So this attention map either doesn't match anything well, or it might match two different objects at once, which is again not good because we want our model, the queries, the outputs of our model to predict just one object per output. So we'll actually penalize the model if one output sort of represents two objects at once. So this is not good. And basically these queries, like the reason the network takes so much to train and the reason it doesn't work that well in the end is because we hoped that these randomly initialized query vectors will be good enough just to learn where to pay attention to, but obviously it's not. So let's try to change that. So there was one work called conditional Detr where the researchers tried to use something different for these object queries to make it to make the attention work better by just explicitly focusing on just precisely one object in the picture. So it has one center of attention, and then the attention mask will slightly degrade over some coordinate, so it has some size as well. And it worked better than the original Detr, but then it doesn't take scale of the objects into account. So some of the objects might really be really big, taking up entire picture. Some of them might be really small. And we also want to take that into account in our attention mask. So in DAB Detr, we also have that. So we try to construct object queries and the entire attention mechanism in such a way that it gives a strong prior about what sorts of objects there are. So they can be big, they can be small, they can be wide, they can be tall. They can be located in different parts of the picture. And we want to give that to the network explicitly to start the attention mask with this instead of random multimodal blobs that don't match anything too well. So we want the model to start with this, and then if it's needed to do proper object detection, to train something else on top of that. So this is the goal of the entire paper, to modulate attention in such a way as to match our expectations of where the model should pay attention to based on how objects look in real life. And so this is the overcomplicated image from the picture explaining all the little details about how this actually works. So how exactly do we use these object queries? How do we use cross-attention to make that work? Don't worry, we'll go over all of these details in this video. Okay, now discuss what those anchor boxes are and what does it mean that dynamic anchor boxes are object queries? So this is a slightly simplified scheme of what we've just seen before, with only the necessary components actually pictured here. So on the left, we have our encoder output. So it's basically refined representation of an image that we will use as this content component on every decoder layer. And so when we just start, we actually have two main inputs to the decoder layer. So one of them is called target, and initially it's just initialized at zeros. And then after the first layer, the same target will be the output of the previous layer. And then we have the queries. And in our case, the query is just 4 numbers now. So height, width, x and y coordinates of the bounding box. So this is what we mean that anchor boxes are queries. So these 4 coordinates, they are part of the model. So they are randomly initialized and learnable, but they do not depend on the picture, which is why we call them anchors. They are like priors to the shape and size of the object and the position of the object that we have before even seeing the picture. But obviously we have, in our case, 300 different queries. So we have 300 of these trainable anchors. So somehow, and how exactly we'll discuss a bit later, we pass these anchor boxes, these 4 numbers, into the decoder layer as queries to participate in the actual attention. Apart from that, the actual decoder layer output is summed up with these anchor boxes. So if you recall, in the original Detr, every intermediate layer output also participates in the loss. So it is being projected down to class probabilities and 4 bounding box coordinates. So we do this projection to 4 coordinates and then sum it up with these prior anchor boxes that we had. And we use that in loss. So there's a couple of ways to look at that. So first of all, these anchor boxes are like priors. So you can think of them as bounding boxes that we start with before we have even seen the picture. So maybe you have this red one that says, I'm looking for evenly shaped square objects somewhere near the center of the image. And so the next layer, because of this sum, because of the residual connection, instead of predicting just 4 bounding box coordinates from scratch, it will try to predict the error. So the first decoder layer will focus on saying that, oh, actually, it doesn't look that it's exactly square, but maybe we'll need to reduce the size a little bit and move it slightly to the left, and then it will be a better match for the object. So now we have this prior anchor box that is independent on the image itself, and the first layer predicts the error of that. So how do we move this prior anchor box to match our object better? And then the next layer will predict the error on top of that. So maybe we still are not precise. Maybe we'll need to move this one here, for example, and so on. So we will update this prediction layer by layer. Another way to look at this, this residual connection basically is during the backward prop. So when we have the loss, when we compute the gradients with respect to the loss, this plus sign here, this residual connection, basically means that half of the gradient will flow here and update the actual decoder layer. And then half of the gradient will go here and update our initial anchor boxes, which means that the 4 numbers that we just randomly initialized, after some training, they will actually correspond to real coordinates and height and width of bounding boxes for the objects that matched well with this query at least. So thanks to this residual connection, we actually make sure that these 4 random numbers are not just random, and we train them to actually represent coordinates and scale and shape of the object. Okay, so now we have our queries, which are now 4 numbers corresponding to x and y coordinates and height and width of the bounding box. And thanks to this residual connection to the layer output, that is connected to the loss, we make sure that these 4 numbers are not just random, they're actually trained to represent coordinates and scale and shape of the real object. Now we want to use that in our decoder in such a way as to have positional attention prior. So depending on where the center of the bounding box is, to say that the model should focus its attention around this center. So this is an updated scheme of how it will look like. So the green boxes here represent something that was added with respect to the last slide. So now we have these 4 numbers corresponding to anchor boxes, and then we expand them into 128 coordinates each using this sine cosine positional embedding. And this is the same process that actually happened in encoder. So when we flattened the image, we lost the positional information. And to compensate for that, we also have this content positional coin, where also both X and Y coordinate had 128 embedding corresponding to them. And so, as we'll see later, during the actual attention calculation, they will interact with each other. So we had 4 numbers as the anchor box. Each of these numbers got converted into this 128-dimensional sine cosine position embedding. So this is a reminder of what a sine cosine positional embedding is. So here, X coordinate represents just the position itself. So is it element number 1, element number 10, element number 100, and so on. And then Y coordinate here represents the coordinate within the embedding. So we have 128 different coordinates here. So the first coordinate is basically a really high frequency sine. And then the coordinate somewhere in the middle is also a sine function, but it's just much longer. So it changes much more slow. And then the final one hardly changes at all. So you can't even notice that it's a sine function now. It just slightly grows over the entire positional range. So we had this process in our content. So every pixel in the encoder output will have this X and Y positional embedding associated with it. Now we do the same for all the 4 anchor box coordinates. One difference with Detr here is that instead of just taking the content embedding, something from the actual picture and the positional embedding, we just computed the sum. So we summed it all up, getting this 256-dimensional embedding similar to the dimension of the content embedding, for example. So here, instead of summing it all up, we just concatenate them together. So we're not mixing these signals. We have first 256 coordinates corresponding to just X and Y coordinates of positional embedding, and then the last 156 to the actual content. So we are only using X and Y coordinates of our anchor box here. So we get 256 position embedding for that. And we put it in this final vector that will participate in the attention on the same position as this X and Y positional embedding from the content, which means that during self-attention, the 2 positional embeddings will interact with each other. So this is the same as saying that we have some coordinates in this vector that will correspond to content here and target here, and they will have some cross interaction between them. And some coordinates will correspond to positional embedding of the image, and then positional embedding corresponding to our anchor box X and Y coordinates, and they will interact with each other. Now, curious thing that is really useful here about these sine cosine embeddings is that when we calculate attention, when we do the actual dot product between 2 elements of these sequences, it is maximal when positions are close to each other. Now, let's imagine a sine function, right? So let's say I've gotten a point somewhere here, and it's positive. So if the second point is also here, then during computing dot product, we multiply 2 positive numbers by each other, and we get, again, a positive number. So the dot product increases. If we had 2 points that are close to each other but negative. We multiply one negative number and another negative number, and we get positive number. So again, this combination contributes to increase in the total attention. However, if one of the numbers is positive and another is negative, and you multiply them, then the total result is negative. So this reduces the final dot product and the attention between such 2 points. So if we only had just one sine function, then the minimal of dot product will be observed when the difference in positions is exactly 1/4 of the period, but then it will be periodic. So eventually it will rise up to maximum again, and then to minimum, and so on. This is like 2 waves on the sea interfering with each other. However, if you have several sine functions with different frequencies on top of each other, then the minimal of one sine function will certainly, almost certainly, not correspond to the minimum of another. So instead of this periodic behavior where you first get a minimum and then get a maximum, you just get decaying overall dot product as you move away from this position. And this is actually the same as you might observe with light. So coherent light, like a laser or just light of one color, is the same as just having one sine function contributing to the signal. And with coherent light, you actually have this interference. So this is, I think, the experiment that was observed back by Newton, where you have these periods of increasing and decreasing intensity of light. But then if you have non-coherent light, and a good example of that is just regular day white light, instead of this, the intensity just slowly decays as you move away from this center. And this is what happens in our case. So when we have positional embeddings for the content and then positional embeddings for our anchor boxes, the dot product, which contributes to the attention mask, is maximal when they are equal. And then when you move them apart, the dot product and attention weight will start decreasing. So it will go down as you move away from this point, which is exactly what we needed. So we wanted our anchor boxes to be like a prior for the position of the object. And then if the real object is away from this position, the attention weight does decay. And once again, this is achieved by the fact that we have concatenated the content part of the embedding and the positional part. So now when we compute the attention mask, when we compute the full dot product between two vectors, dot product is just element-wise multiplication, which means that coordinates corresponding to positional embedding of the content will only be multiplied by the coordinates corresponding to this positional embedding of x and y coordinates of the anchor box. Okay, so now we have our anchor boxes as queries, so just 4 numbers, x and y coordinate, height and width. Thanks to the residual, we actually train them to make them represent the coordinates and the size of the object. Now, thanks to these positional sine cosine embeddings and this peculiar dot product between the content position embedding, we get this attention prior behavior where attention is modulated in such a way as you have content part and positional part does focus on specific coordinate and then decays as you move away from it. Now let's talk about the size attention modulation. So how we encode the height and width and make sure we are able to focus on objects of different scale and shape. So the only new thing on the diagram is this division operator. So in the original anchor boxes, we had height and width as well as x and y coordinates. Now we get the sine embed for these x and y coordinates, and we divide that by height and width. So honestly, I've read the paper like a few times and I've read the code, and this is what they do. They just divide the sine cosine embedding by height and width of the anchor boxes. Somehow that makes it modulate the size. So they take the sine cosine embedding, they multiply it by this h predicted divided by h and w predicted divided by w. So h predicted and y predicted is like a number that is trainable. So they actually get the embedding and then a multi-layer perceptron on top of that to predict this number, which is a way for the network to decide on its own height and width, but then divide by the actual height and width of the anchor box. And so supposedly, as reported by the paper at least, this should allow the attention to be modulated by size and shape. So it can make the total attention mask, at least the positional part, either smaller or bigger, or maybe make it really wide, or maybe make it really tall. I honestly don't understand how they get from dividing the position embedding by height and width to this sort of modulation. But I tend to believe that it is indeed what happens. So if you know how this happens, maybe this is something that I've missed in the sine-cosine embeddings themselves. Please comment, because I honestly reread the paper several times. I don't understand it. Now, finally, the last component of this is dynamic layer-by-layer update. So we started with some anchor boxes, coordinates and positions and shapes that are independent on the picture. They're just focusing on one specific shape of one specific location within the image. But then we have this decoder layer that predicts the actual bounding boxes of the objects we see on the picture, or rather the error with respect to the original anchor boxes. So now, after this residual connection, the output of that is our first estimation of the actual bounding box for the object. And apart from being used in the loss, we also use these new anchor boxes as our new prior for the next decoder layer. So you can think of this as step-by-step process, where you start with some image-independent approximation of the bounding box. Then after the first layer, you modify it a little bit to actually represent the bounding box of the current object. And then you use this new, better approximation in the attention modulation of the next layer, and then arrive at even better representation of the bounding box, and so on. So you refine it layer by layer, but you also make sure that every layer uses the current best approximation of the anchor boxes for the actual attention modulation. So once again, this is how it happens. Decoder layer, the output of that is the sequence of 256 dimensional embeddings. Each of them, after every intermediate layer, is projected to 4 bounding box coordinates and 91 class probabilities. Then we have this residual connection where 4 bounding box coordinates in the output are added to the input, so to the anchors for the first layer and the input of the previous layer after that. And then we feed that into the loss to make sure that every anchor box in this intermediate layers is actually trained to be anchor box, so x and y coordinates, height and width. And also these new approximation of the bounding boxes are also used as queries for the next layer. So we update our estimation of the size and position of the object, and we use that updated estimation to modulate our attention. Now, finally, let's talk about results. So this is a picture from the paper that is really nice to look at. So they start with just the normal Detr, and we can see how it trains and what final quality we achieve. And then they compare it to conditional Detr that only uses this positional modulation but doesn't use size modulation. And we can see that it trains much faster and also arrives at a better result. And then the DAB Detr, which trains even faster and gets even better final results. So the paper managed to get plus 2% of multi-average precision on COCO dataset. We can also combine different techniques. So we can combine deformable Detr and dynamic anchor boxes Detr to achieve an even better model. And by now in 2024, we also know that these techniques combines well with everything else, like vision transformers, denoising, deformable attention. So current state of the art uses all of them at once to have the best quality currently available in the market. So one comment about the comparison of these anchor boxes to what we had in YOLO, which also used anchor boxes. So one key difference is that in our case, anchor boxes are trainable. So we are not explicitly coding down some anchor estimations, and that is prone to error. We might be mistaken. We might not do that properly for the current data set that we have. Instead, we let our model learn that. Then, on top of that, it's only a part of attention. So even if we had these 300 queries that should cover all the possible shapes and sizes, even if we get a new piece of data that the model maybe haven't seen before, like an unusual shape, unusual scale of the object, and we don't really have anchor box that matches that well, still that's only half of the attention mask calculation. So the other half comes from the content, comes from the image itself. So the model might still choose to ignore that. The model might still detect objects well in that case. So these anchor boxes are only used as a prior, but not as a final state. So in YOLO, if the object doesn't match, you will not even see it in the model. In this case, you still have content part of the attention mask, so the model might still be able to deal with that. Dynamic anchor boxes, they do not introduce more trainable parameters. So one thing that happens is the size of the embedding that we now pass to the decoder is twice higher. So we had 256 in Detr. Now, because of this concatenation of content and position embedding, we have the embedding that is twice bigger, which does make it slightly slower to do cross attention in the decoder. But decoder itself is more lightweight than encoder because the sequence length is much smaller than that of the decoder. So it doesn't add too much to the complexity of the model, but it does make code a bit more complicated. So we started with Detr, which is really clear in terms of how the code looks, how uncomplicated it is in terms of main concept used. So now after adding deformable attention, denoising, and dynamic anchor boxes, that starts to look like a mess. So it's really hard to work with that, unfortunately. So this is it for today. I hope my explanation was clear. Do let me know if it was, and if you're even interested in videos like that. Apart from that, I have my channel, which I created as maybe a learning path for people to learn computer vision and hopefully in the future other machine learning areas as well. So it has a lot about modern object detection. So I'm currently on the way of making videos about main components used in the current state of the art. So I've started with Detr. I've explained how it works, how it compares to YOLO. I had a video about reading the code for Detr. Then I have a video about deformable Detr, which is a slight modification of the attention mechanisms to make it better, to make it more lightweight, and the code and the video about reading the code of that as well. So today I did dynamic anchor boxes Detr, and the very next video will be about reading the source code for that and training your own model. So we'll look at much more details about dynamic anchor boxes. If you are still unsure about how some of the parts connect, it might be easier to just look it up in the code, which is what we'll do in the next video. And then I want to continue and look at other concepts like vision transformers, swing transformers, and coDetr that actually allow us to have this state-of-the-art model. Apart from that, there is like an earlier part, which is just introduction to computer vision. So it starts with something really simple, image classification with PyTorch, which is dense layers that you can sit down, code yourself in half an hour, and it doesn't use any complex code, complex concepts. Then on top of that, we've added a lot of deep learning fundamentals like convolutions, activation functions, parameter initialization, batch normalization, residuals, all of that, culminating in a big project called ResNet, which was a winner of 2015 ImageNet competition, which basically arrived at above human performance on classifying high resolution images, which was really great indication of progress at the time. And so I have a video about reading the code and training the model like that yourself. Other than that, I also started a branch about generative AI. So the very first video is already out, and it is about neural style transfer. And then on top of that, I want to go through most of the modern good image generation techniques, such as variational autoencoder diffusion, then stable diffusion, then conditional diffusion, where you actually have some sort of text prompt, then that lets you generate an image that you want, and so on. So there's a lot to cover. I hope my videos are useful to you. So stay tuned and see you soon.